In this video, I want to continue our discussion of stellar evolution, which is just a term we use to refer to the changes that a star undergoes over the course of its life. We talked about the fact that a main sequence star, kind of in the middle of the main sequence, like our sun, or a star a little bit less massive, a little bit more massive than our star, will live for billions or even tens of billions of years. Our star probably has about a 10 billion year lifespan on the main sequence. We also talked about the fact that more massive stars, which burn hotter and brighter, actually live for less time. A big, massive O-type star might only live for a few million years because its core is being squished so hard that hydrogen is fusing so fast into helium, it burns up more quickly. Whereas a star with less mass than the sun, like a K or an M type star, which might be half as massive or even a third as massive as the sun, because the hydrogen in its core is being squeezed more gently, fuses more slowly, and those stars actually last longer. You can almost think of it as the difference between an SUV and a little tiny compact car, right? A little tiny compact car has a smaller gas tank, but it's also more fuel efficient, so it can go further on a tank than a great big Lincoln Navigator with a bigger gas tank, but that burns its fuel more quickly. The evolution of low-mass stars is pretty straightforward. A star that's maybe half as massive as the sun will go through the same steps we talked about for the sun, except that when the hydrogen fusion starts to slow down in its core because of the helium getting in the way, that will cause the core to collapse, that will heat up the region around the core, that will cause the star to expand into this shell-burning subgiant phase. But there's not enough mass to ever squeeze that core enough to make it have a helium flash. A star half as massive as the sun will never have a helium flash. It will never expand into a giant. It will never go beyond fusing hydrogen into helium. So those stars will just evaporate, their outer layers fade out into a white dwarf without ever going through this actual giant phase, post-helium flash. So that's what the life of a low-mass star looks like. Even lower-mass stars, like an M-type star that's maybe a third as massive as the sun, might not ever even reach the subgiant phase. When they run out of hydrogen fuel, when the helium starts to get in the way, their fusion just kind of slows down, and they just get dimmer and dimmer and dimmer and cooler and cooler and cooler. So red dwarfs, M-class stars, which are some of the most common stars in the galaxy, may just actually just fade away without ever doing anything fun or interesting at the end of their life the way our sun does. What about these high mass stars? What about stars at the hot, bright end of the main sequence that burn themselves out very, very quickly? Do they just turn into giants and then white dwarfs the way the sun does? No, not exactly. The end of the life of those stars can be much, much more dramatic than our sun, and it involves more steps than our sun. It's a similar process that starts out a similar way. We said that in our sun, the hydrogen fuses into helium for billions of years, and eventually we will reach a point where the rate of fusion starts to slow down, the core starts to cool, gravity starts to win, gravity squeezes the helium together, and helium can fuse into beryllium and carbon. That, for our sun, is the end of the line. The beryllium and carbon start to get in the way, the rate of fusion slows down, the core temperature drops, the outer layers just kind of cool off and evaporate away, and you wind up with this exposed, mostly carbon or largely carbon core of our sun will eventually be the sun's white dwarf. For stars more massive than the sun, though, they can continue this process over and over. The rate of helium fusion starts to slow down. The core starts to cool. Gravity starts to win. Gravity starts to squeeze that core of beryllium and carbon until a more massive star can actually have what's called a carbon flash. And it can start to fuse carbon and beryllium into the next phase of elements. Carbon and beryllium can be fused into oxygen. Carbons can be fused together into neon and magnesium. Heavier and heavier elements on the periodic table. A star more massive than that, when the carbon fusion starts to slow down, can squeeze those oxygens and neons and magnesiums together and cause them to fuse into sulfur and calcium and iron. So as we go on and on and on to more and more and more massive stars, they can have not just a helium flash, but a carbon flash and a neon flash, and continue fusing heavier and heavier elements in their cores. Our sun will not do this. Helium into carbon is the end of the line. As we get to heavier and heavier and heavier elements, it requires more force to squeeze them together and fuse them. Take 2 carbons. Our sun's going to eventually fuse heliums into carbons, right? Each of those carbons has 12 protons in it. Each of those protons has 6. Carbon 12 has 6 protons, 6 neutrons. So here I've got a carbon 12, here I've got a carbon 12. What is the force of repulsion between those? Well, it's 6 protons times 6 protons, or it's 36 times greater than the repulsion between 2 hydrogens. Our sun will never be able to squeeze those carbons 36 times greater than it can squeeze 2 hydrogens. So it will never be able to do this and this. But more massive stars 5 times, 10 times, 20 times, 100 times more massive than the sun, will be able to go through these successive phases of nuclear fusion until they reach iron. An iron nucleus is special. And in order to understand what happens next to these stars, we have to understand what is special about an iron nucleus. This is a little bit complicated, but we have to think about why we get energy when we fuse hydrogen to helium. It's because a helium nucleus with those 4 protons stuck together and turned into 2 protons and neutrons. 2 protons and 2 neutrons. A helium nucleus is more stable than 4 hydrogens separate. Those hydrogens are happier to be in a helium than they are to be separate. One way to think of it is just imagine tossing 4 magnets into a drawer and then giving it, or into a box and giving it a shake. What's going to happen when you open that box? Those magnets are going to be stuck together because that is the lowest energy state of those 4 magnets. They're happier to be stuck together than they are to be apart. We can encapsulate that happiness of those things to be stuck together in terms of the nuclear binding energy, how much energy holds the nucleus together. And we can go and make a graph from the lightest elements in the periodic table, hydrogen, helium, beryllium, boron, or lithium, beryllium, boron, to the heaviest elements in the periodic table, uranium, plutonium. And we can make a graph of the nuclear binding energy as a function of how many protons they have in their nucleus. That graph looks something like this. If we graph every element in the periodic table and every isotope of every element in the periodic table, from hydrogen and helium to carbon, nitrogen, and oxygen, in the middle you have kind of iron, cobalt, and nickel, heavy elements like platinum and gold and mercury, and finally at the end, uranium, neptunium, plutonium, the heaviest elements in the periodic table. This curve looks like something like this. The light elements are less tightly bound. The middle elements are most tightly bound. Okay, so this graph goes from less tight to more tight. I'll explain in a second why we graph it that way instead of the other way. And then the really, really heavy elements like mercury and radon and radium and uranium, neptunium, plutonium are also less tightly bound. That's why they're radioactive, by the way. These elements at the top of the periodic table are happier to be in pieces than they are to be stuck together. That's why a uranium nucleus will spontaneously split itself in half. That's how a uranium bomb works. That's how nuclear fission, splitting apart heavy radioactive elements, gives off energy. You can think of this graph, the reason we graph it from low to high instead of high to low, is you can think of it as a roller coaster, right? If you put a car on a roller coaster, it will roll to the bottom of the hill. That's where it is happiest, right? If you put it here and let it go, it will roll to here. A nucleus is happiest on this diagram to be closest to this point. Here, it becomes more stable by fusing together with other lighter elements to make heavier elements. So hydrogen fusing into helium or helium fusing into carbon results in a more stable atomic nucleus. Uranium splitting in half results in a more stable atomic nucleus. That means that at this end of the periodic table. Fusing nuclei together gives you a more stable nucleus, and that releases energy. At this end of the periodic table, splitting nuclei apart results in a more stable nuclei, or two more stable nuclei, and that releases energy. That's why splitting uranium or plutonium makes a bomb, or if you do it more slowly, makes a nuclear power plant. That's how a nuclear power plant works. We dig up uranium from the ground, we purify it, we take out the most unstable isotopes, we put them in a big pile, they just heat up from all those nuclei splitting in half all by themselves spontaneously, and then causing other nuclei to split in half in a chain reaction. The middle of this diagram is iron, more or less. Iron is the most stable atomic nucleus. Neutrons and protons are happier to be in an iron nucleus than they are to be in any other nuclear system. That means you cannot get energy from splitting iron in half. That uses up energy. And you cannot get energy by fusing anything with iron. That also uses up energy. It's not to say you can't cause nuclear fusion to fuse iron into something else. You absolutely can. But that process is going uphill. It takes energy to do that. It doesn't release energy. That means that once in a star we make iron from nuclear fusion, that's it. We can't make any more energy by fusing irons into something else. Which makes iron the end point for the process of nuclear fusion, at least in terms of generating energy. Now, the star doesn't know this. Stars don't know about nuclear physics. All they know is gravity squeeze, which means when there's a bunch of iron in the core, gravity will just squeeze that iron. The question is what happens. Before, when we squeezed hydrogen into helium, it caused nuclear fusion. That gave off energy, which caused heat, which made the star want to expand. When we fused helium into carbon, that gave off heat, which caused the nucleus to want to, or caused the core of the star to want to expand. When we fused carbon into oxygen and neon and magnesium, that process of fusion gave off heat, which caused a thermal expansion to combat the gravitational collapse. But if we try to fuse iron into something heavier than iron, that won't generate energy and it won't create heat. It will actually use up energy. So when a star reaches this point, it will fuse iron with other things, absolutely, in the core. It doesn't know any better. But that process stops giving off heat. And this leads to a runaway chain reaction where as iron fuses into other things, that doesn't generate heat in the core. That takes away heat from the core, which causes gravity to squeeze the core in more, which causes more irons to bang together, which causes more fusion, which causes less energy to be created, which causes gravity to squeeze it more, which causes a catastrophic cooling, which causes a catastrophic collapse. When a massive star reaches the point where it tries to fuse elements into things heavier than iron, gravity suddenly has nothing to stop it from squeezing that core in as much as it can. Except matter is not infinitely compressible. If you've got a core made of iron and heavy elements, carbon, nitrogen, sodium, neon, whatever, they're all made of protons, and you can't push those protons any closer than a certain amount. Or can you? There's also a bunch of electrons in here. You can't push two electrons infinitely close together. The force between two electrons, like charges repel. They don't want to be that close together. At some point, the core will reach the maximum density that you can compress matter to, and you can't compress it anymore. And then the material falling in hits that, and what happens? It can't compress it anymore. So what happens is it bounces off. This causes a shock wave that actually blows the star up. So the last thing to happen to one of these massive stars is that it explodes. And the explosion is caused by the catastrophic runaway cooling in the core when you try to fuse iron into things heavier than iron. That explosion is called a supernova. A supernova is a star that has blown itself up, and that explosion is caused by the rebound of material trying to fall into the core when the core itself has reached the maximum possible density. I've got a really silly example to show you an analogy for how a supernova works. Maybe I'll record a separate video showing that. Supernovas are extremely energetic and extremely bright. This is an artist's conception. This is just an image I made of what happens when a star in a galaxy goes supernova, which is, for a few weeks or months, that one star, former star if you prefer, becomes as bright as all the other stars in the galaxy together. The star gets billions of times brighter. It gives off huge amounts of energy in that process. It is in this explosion that all of the elements that have been fused in the star up until then are released. And all of the elements in the periodic table above iron, there's iron Fe, are fused in the process of this final collapse and an explosion of this star. In fact, all of the elements that you are made of, that everything around us, that the Earth is made of, were once inside of a star, except for hydrogen and helium. Shortly after the Big Bang, the only elements in the universe were hydrogen and helium. All of the carbon in your cells, all of the nitrogen that you are breathing, all the oxygen that you are respirating, all the calcium in your bones came from fusion, nuclear fusion, inside of a star, billions of years before our solar system even formed. Not fusion in the sun. The things fusing in the sun are just stuck in the sun. All of the heavy elements that the Earth is made of, all the aluminum that your laptop is made of, all the silicon and the computer chips and the sand at the beach, all of those nuclei were fused inside of stars that lived in previous generations before our sun ever formed. Everything in the periodic table up to iron can be fused in a regular old star, and it leaks out in the process of the outer envelopes of the star evaporating late in its life, the solar wind just kind of blasting out these elements. But everything heavier than iron, okay, nickel, silver, mercury, gold, platinum. The reason everything down here is kind of more rare than everything up here is because the only place that these things get created in the universe is supernova explosions and other really, really exotic energetic phenomena like colliding neutron stars and stuff. So the reason gold is worth more than aluminum is more common because it's made in regular old stars, and silver and gold are only made in supernovas. So if you have a piece of gold jewelry, this is my wedding band, it's made of white gold, okay? Every one of those gold atoms is the product of supernova explosions and neutron star collisions and incredibly energetic phenomena that happened before our solar system even formed. Okay. So all the heavy elements are created by these violent astronomical phenomena that are relatively rare, which is why all the heavier elements are relatively rare. This is what a supernova explosion looks like well after it happened. This supernova explosion happened, I think, at 1054 is the date of this supernova explosion, so the 11th century, maybe 1056, I don't know, it's the 1050s. And we know the supernova explosion happened in the 11th century because people saw it. There are drawings of a bright star in the sky recorded by astronomers in ancient China, recorded by astronomers in the ancient Middle East, recorded by Native Americans, painted a picture of a star on a rock next to the moon in the exact place that this explosion happened. When a new star shows up in the sky, that's a big deal. Remember, to the ancients, the sky was supposed to be always the same. The word nova means new, okay? When a star suddenly appears in the sky where there wasn't one before. This is what it looks like now when we take a picture with our most powerful telescopes. It looks like an explosion. It looks like something right there blew itself up. We can actually take a picture of this explosion every few years and measure how fast it's expanding, and then extrapolate backwards and find that it happened on the year that we saw this explosion happen. This is called a supernova remnant. We see a bunch of these. We know that stars blow up. We see it happen. We see what it looks like after. And this model of stellar evolution is consistent with the energy and the appearance of these explosions. Seeing a supernova explosion is very rare. With a powerful telescope, we can see them in other galaxies. As far as one that you can see with your eye, they tend to be something that happens every 500 years or so. Any red giant star that you see in the sky could go supernova at any moment. Any blue supergiant star, any of the two stars in Orion, the two brightest stars in Orion, Betelgeuse is the top shoulder and Rigel is the bottom foot. Either of those stars could blow up tonight. Well, if we saw them blow up tonight, that means they blew up hundreds of years ago when that light from that explosion first left them. But any giant star, supergiant star, is a candidate for one of these explosions. If Betelgeuse went supernova tonight, you would be able to go outside and read a book by the light coming from Betelgeuse. That's how bright it would be. It would give off so much energy, so much radiation, that it would be like every human on the earth got a chest x-ray from the gamma rays and x-rays coming from that supernova explosion. Which is fine, like one chest x-ray isn't harmful for you, right? But that's how much radiation we would get from that supernova explosion. Could it happen in your lifetime? Could. Will it? Probably not. Just a couple of years ago, Betelgeuse did something really weird where it got dimmer for like 9 months than it usually is. And people thought, oh, is something up? Is it going to blow up? But then it got brighter again. We think it was just like an outburst of gas that kind of got in the way and made it appear dimmer. Anyway, there's no way to know when a star is going to blow up because all that stuff is happening in the core. So they happen when they happen. So I think I skipped over the question of what happens to these stars as they go through this helium flash, then carbon flash, and then oxygen and sulfur flash, is they get bigger and bigger and brighter and brighter and brighter. And that's what a supergiant star is. A supergiant, our sun will have its helium flash and become a red giant. More massive stars will go through these successive flashes and become supergiants, and then eventually they blow up and they are supernovas. One question we can ask is, what's going on here? What's going on in the middle of the Crab Nebula? What's left behind, if anything, when a star blows up? Is it just gone? Is this the star? It's just blown up and there's nothing left? Well, I said that what happens in this process is the core collapses as it starts to fuse things into elements heavier than iron. That sucks up all the energy that causes the cold. Gravity wins, the core collapses. And I said that collapse stops when matter reaches the maximum possible density it can reach. And the explosion is the infalling matter bouncing off of that and blowing the star apart. But what is this? What is this maximum density that matter can possibly reach? It turns out that there's two possibilities. One is a thing called a neutron star. The other is the thing called a black hole. And we will talk about neutron stars and black holes in some separate videos. We call these things left over after the supernova explosions supernova remnants. And neutron stars are one kind of supernova remnant, and black holes are another.